Okay, thank you for the organizers for the invitation. Really happy to be here. Really happy for the evening booze. Am I on the camera? Okay, this is on best time identification through. Yeah. So it's a problem of best time identification through fluid-based methods. That's what we reduce. But it's kind of in the broad topic of multi-arm bandits. Hence this picture right here. So this is what I think of when I think of multi-arm bandit. It's a bandit. He has all the things that I value. So there's coffee, the lower bounds, and you'll see why. And then there's my cell phone. So, but multi-arm bandits, let me not talk much about this. So this is joint work with my student Agdev Bandyopadhyay, and then Shubhada, Karthike, and Arun. We worked on this when I was at Google Research last year. Okay, so this is the problem. So it's a very simple problem. So the first two slides, if you get these right, then whatever you see later, you can link it to this. So you don't get too far away. So there are k unknown probability distributions that can be sampled from. We don't know the distributions, but we can generate samples from them. You want to find the distribution with the largest mean using fewest samples while keeping the probability of false selection to a pre-specified error of delta. So you told me 1% error you can accept. So now I'm going to sample these from these probability distributions and tell you which one has the largest mean as quickly as possible. That's the game. So for example, you could have 3 coins. This one has 0.8 probability. I don't know that. This one has 0.6 probability, 0.9 probability. I'll flip these coins and I'll learn and I'll figure out which one has the largest mean and then inform it. So, I've been saying in between that I'm an outsider to networks, and then you're probably wondering why am I invited. But this learning stuff is not that far away. It has some utility to what happens in network. It's kind of when you do, for example, reinforcement modeling and all of that, reinforcement learning, this is kind of a basic model to get ideas from. So in that sense, some of what I'm going to say is kind of generic. So my objective is I'm going to give an intuitive overview. So just my own kind of way of thinking about things. And then we'll propose optimal top-2 algorithm where we'll come up with a fluid limit and we'll chase the fluid limit. Again, I'll try to point out specific things, but also generic things that are more broadly useful. Okay, just to drive home, maybe 5 years ago I would have put bitcoins or dollars or euros, but now I'm retiring, so I just look at pesos. So everybody should be with me on this. There's no issue on this, right? I flip these coins one by one sequentially. These 3 coins, I want to figure out which one has the highest probability of heads. That's the game, right? So, and stop, sequentially I stop and I'm 95% sure. All right, so some applications of this stuff is kind of, it's very simple, but it's widely applicable. That's the nice part of it. So applications are important. So you're given 4 vaccines and you want to know which one to give to patients. So before you finally roll out to the whole country, you want to figure out which one is the best one. So this would be fitting into that setting. All of this multi-arm bandit work goes back again to a biophysicist in the 1933, Thomson, who said that you can get considerable savings in terms of lives of people by administering the drugs efficiently, figuring out which drugs work better. Some other applications, placing advertisements on Google search. So these kind of algorithms are being running in the background when they decide what is the advertisement that you're likely to click more, which one has a higher probability. Web constructions, amongst many options. Recommendation systems, so movies to recommend, which movies again have a higher probability of being preferred by you. Facebook posts to show, newspaper articles to bring to your attention. So all that's wrong with the world today, the shrinking of democracy, the polarization, these algorithms have a role to play in it. So, okay, travel route to recommend amongst many. So this is interesting. I don't know how many of you are familiar with cricket, but you evaluate a cricket person, so you're an expert and you see a person bat for maybe 1 innings, 2, 3 innings, 4 innings, and then you decide, okay, this guy is selected, this guy is not selected. So if you have to separate probability of 0.6 coin from 0.4 coin with 95% certainty, you need 150 samples thereabouts. So lots and lots of samples. So 3 or 4 samples that you typically see to make decisions. 3 or 4 reviewers, what they think of your paper is not so important. You need 150 reviewers to tell you that your paper is really bad. So that's a bit of things. But of course, I mean, so you have to ask yourself, okay, maybe each ball is telling you something. So maybe 150 balls is enough. So those are subtleties here. But people don't talk about this kind of, in probability, there's this issue of small samples, that we are biased by small samples. Okay, so let me just first start by giving you a popular algorithm so you get to see some of the kind of simple ideas there. And this is going to rely on our old friend Hofding. Do all the students know what Hofding inequality is? You see this before? Oh, good. I've been in audiences where nobody's heard of it. So xi takes value -1 to 1 with 0 mean. So you're talking about, okay, the average taking a large deviation. And what you're looking for is a uniform bound. This is not like a Chernow bound, which is distribution specific, but bound which works for all distributions which are in this boundary interval. So you get this uniform bound to Hofding's. And that's very useful in exponential decaying, because now you can come up with, what we are going to do is adaptive. It's going to depend upon, on the memory as we go along. So you want to have algorithms which kind of work in that setting. So you want to have these anytime bounds. So there exists time t, so that this sample average exceeds alpha of t. Alpha of t is right here. It's well chosen. It's deterministic, 4 log t 1 delta by t square root. So this you can just, have this union bound here and get a bound, sure this is less than equal to delta. So these tubes that we construct around sample averages are very useful to think about things. So these concentration inequalities, that's what I was asking Vivek also, that in even stochastic approximation, maybe there are concentration inequalities, and that's where things are much easier to see. And yeah, I'll illustrate that through these pictures. So this is the tube I'm talking about. So this is a picture worth keeping in mind to begin with. So these are number of samples, 5, 10, 15, and so on. Sample average lies in this tube. This is mu plus minus alpha t with probability 1 minus delta. So the point of the name of the game is you've given me 1% error that I can live with. So I construct these tubes so all the bad things happen outside this 1% of error. So then I don't have to worry about bad things. I just do deterministic analysis. So that's the charm of this stuff. So what does this mean? So what do I get from here? So this is the algorithm. This is from 2006. There are many others, but I'll just focus on this simple one here. Successive rejection algorithm for arm rewards in 0 to 1. So sample each arm once. And at any time t, there'll be active arms and there'll be some arms which have been fathomed. So active arms, you sample them once. You look at the arm with the largest sample average. And then if any arm is sufficiently far away from this sample average, you fathom it. You throw it out. Right? And how much larger? 2 alpha t. Alpha t is again given by this formula here. And that's the algorithm. You carry on until you're left with just one arm. And that's the best arm. Right? So it's simple, right? And why does it work? Because you'll see from the tubes, we'll restrict ourselves to tubes. We'll construct these tubes in such a way that with 1 minus delta probability, sample averages are going to remain in those tubes. And now, if you're in those tubes, and if you're on that good set, you'll never throw away the best arm. And eventually, you'll throw away every other arm. That's the argument. So here, for example, you can see that best arm, x bar 1t in this tube is always greater than mu1 minus alpha t. Right? It only shows large deviations outside of this tube. And x bar at for any arm A is always less than or equal to mu a plus alpha t. Right? So x bar at minus x bar 1t is always less than 2 alpha t, because of this quantity here is positive. I'm assuming that the best arm is unique. So because of this property, you'll never throw away the best arm on this good set. That's very nice and clean. And now if I consider a bigger tube, x bar t lying in mu plus minus 2 alpha t, now you see the point where in this bigger tube, the two curves intersect. At this point, x bar 1t minus alpha t is going to be more than this on the good set. And x bar at plus alpha t is going to be less than this quantity on this good set. So by this time, for sure, your algorithm is stopped on the good set. And then you argue that, okay, on the bad set also, it's not going to cause too much, it's not going to contribute too much to the time taken to stop. So that's how one does this kind of analysis. So, delta correctness is assured because on the good set, we are always choosing the best arm. And you can talk about how much time. So that's the question we're asking, how much time it took the sample complexity. In this case, it's easy to see that this point gives you log 1 by delta and then some term here. This is just order optimal. It just gives you an idea of how one can construct algorithms. What's nice about these algorithms is that they're working for any delta. It's non-asymptotic. So I can construct nicer non-asymptotic algorithms. But you get a, to match, yeah.
Is delta the same as the thing for the false positive?
That's right. That's exactly the same delta. That's exactly the same. That's what we use to construct all this.
Use of A is what? Or any A.
Any arm A is mean. Yeah. Yeah. Any arm is mean. So this is the best arm's mean, and this is any other arm is mean. Yeah. Thanks. Right. So, yeah, the point was, but to, so what I'll do now is I'll develop a lower bound that any algorithm which is delta correct satisfies, and then I'll try to come with algorithms which exactly match that lower bound. And we'll talk about good algorithms, etc. there. But that can only be done currently as delta goes to 0 in an asymptotic regime. And in some sense, we'll exploit the asymptotic regime to get insights into the problem. So lower bounds and algorithms that match even the constant in the lower bound. So we want to match even the constant in the lower bound, not just be order optimal, but exactly optimal. Okay, so trivial lower bound in these problems. So suppose each arm receives log 1 by delta to power alpha samples, where alpha is between 0 and 1. Right, so square root log 1 by delta, for example. And the claim is that's not going to be enough. And why is that? Just look at this probability that x bar n looks like A. By large deviation analysis, that's e to the power minus nia. So when I plug in this value of n here, so if n is log 1 by delta to the power alpha, then this probability you can check looks like delta is to the power something which is going to be greater than delta for all small delta. With this exponent, it is going to 0. So not enough samples is what we are saying. If you don't give enough samples, your sample average can be anywhere. You're bound to make a mistake. So log 1 by delta samples one needs. And that goes without saying here. But now let's develop a slightly better lower bound. So this slide, again, I've used for people who've not heard of Sarnoff's theorem before, but let me just say it nonetheless. So green is, let's say, is the true distribution. Takes on 4 point support, x1, x2, x3, x4. I observe IID samples from this distribution, x1 through xn. I compare I come up with an empirical distribution that's this, suppose it's a red distribution. So this red distribution will look like green as I have more and more samples, right? Empirical distribution converges to true distribution. And Sarnoff's theorem says exactly what's the probability of underlying distribution being mu, the green one, looking like it's the distribution nu. It's exponential minus n Kullback-Leibler between nu and mu, right? And there are some terms here, but this is a joke I use here about beauty that, if you see the painting that I make and that Picasso makes, if you see from a distance of 2 millimeters, it looks about the same. If you see from 2 kilometers, it looks about the same. You have to see things at the right resolution. So the same thing here, you see a beautiful thing at the right resolution for Sarnoff's theorem. It's telling you, this is basically telling you the separation between mu and nu. Right? So that's very useful here. So Kullback-Leibler, everybody knows this definition here. Okay, so now that we know the Sarnoff's theorem, so let's do this thought experiment. Where we're going with this is we want to get lower bound. See, the game is we want to figure out which arm has the highest probability of highest mean, right? Essentially, we need evidence to convince ourselves that all the other arms are actually suboptimal arms. We want to stop sampling them once we are convinced about them, and that's when we stop, basically. So how do we get that evidence? This is the thought process behind it. So observe distributions from N1 and N2 samples. This is in the 2-arm setting. So let's say these are the 2 empirical distributions that we've seen. So with high probability, this distribution, and let's just think of this as Bernoulli's for now. This mean will look like the true mean, or this distribution will look like the true distribution with high probability by Sarnoff's theorem, right? And it will look like the mean under mu hat 1 is bigger than mean under mu hat 2. Because, and this is the case where I'm assuming mu1 is bigger than mu2. So this will look, things are as they should be. So this will suggest that mu1 is bigger than mu2. These are means. So that's a suggestion thing. But you're concerned, right? As a skeptical scientist, you want to be sure. So you wonder its likelihood if true distributions are nu1 and nu2. What if what I'm seeing is actually a large deviation? What is the true distribution of nu1 and nu2? Right? Such that m of nu1 is less than m of nu2. So the conclusion was alternate to what I'm seeing. So I need to be careful about that. I need to control that probability, right? So let's look at this set, nu1, nu2. This is the alternative set of alternatives. So worst case likelihood of incorrect assessment It's, by Sarnoff's theorem, this is a heuristic argument. E to the power minus n1 KL mu hat 1 nu 1. Same thing here, nu 1, nu 2 in the alternate set. I look at the worst case here, and this is the probability I want to keep less than delta. Now this mu hat 1 and mu hat 2 in a high probability path I can replace by mu 1 and mu 2. It's kind of an idealized argument because for lower bounds, I assume that I know the parameters. This is not such a, it's not such a kind of a big hand waving thing. This term here, for those who know statistics, this is just generalized likelihood ratio term. So, we just kind of, we want to control that. That has to be small enough, or the ratio inverse of that has to be large enough. That's how these tests work. But in any case, this is a nice way to think about this from Sarnoff's theorem, that this has to be small. So let's come here. Let's look at this as the alternative set. Nu is these k distributions. So m nu 1 is less than some other arm's mean. These are all the alternatives that we worry about, right? So amongst all these alternatives, this is the chance that the alternatives are, are the true distribution, but the data looks like mu I. So this is what we want to control. This one, we want to make this less than equal to delta. So minimize, so that's what I get basically from here. I want to keep this less than equal to delta. That's just saying that this quantity right here, infimum on this set of alternatives, this has to be greater than equal to log 1 by delta. So if I have these many samples which satisfy this property, then I have insufficient evidence. I'll just choose my samples to minimize this. So it's like I have infinitely many linear constraints. I just want to minimize them and come up with a lower bound. So that's a heuristic argument. Now, people here, as ISI people always say that I talk too much heuristic, so where's the actual proof? So the rigorous argument comes from data processing inequality. So this is, I guess, from information theory that Kullback-Leibler distance between probability measure corresponding to X and probability measure Q, another probability measure for X, right? It contracts because there's an information loss when we look at some function of X. So Kullback-Leibler of G of X and Q of X. So that's a very nice inequality. So this is what gives you the lower bound, basically. Everything I said was heuristic. And all I do is I look at that bandit algorithm. So I look at this data. First time I pulled arm A1, I saw this reward, RA1 and A1. I look at till some stopping time T. So this is my random variable X. I look at this under probability measure mu, corresponding to true measure associated with X. And I look at this under probability measure nu, corresponding to alternate measure which belongs to the alternative set. And I apply it here. So Kullback-Leibler of P mu of this sequence of random variables. Again, the probability of this sequence of random variables under measure nu. This will be dominating probability assigned to an indicator of event E under two measures. Kullback-Leibler of probability assigned to indicator of event E. So I choose this indicator event E that true measure is mu, and I make a wrong conclusion. So then this indicator has this probability is less than or equal to delta. That's what my algorithm is guaranteed. And under nu, this probability is greater than or equal to 1 minus delta, right? So that gives me log 1 by delta here, basically, with some constants which I'm ignoring, but it gives me log 1 by delta, essentially. And this term here simplifies to this quantity. It's not so hard to see here. The difference between mu and nu is simply that when I generate rewards, I have different distributions. But given that I've seen some data, where I go next, which arm I pull next, is same under both the measures. It's the same data, so I assume the conditional probabilities are the same. So because of that, this Kullback-Leibler here is coming because I just have different densities for generating rewards, and that gives me this quantity. Let me just say a little bit more about this. So this quantity here is just log of I look at each and every action I took. I went for t time steps. So the density for seeing this random outcome under the two measures, log of that, I sum it up, and now I can do iterative conditional expectation. So one at a time, this log here, d mu a by d nu a under p mu measure, that will have expectation Kullback-Leibler between mu a and nu a, and then the indicator that at was arm A. That's for each term here. I'll just sum these indicators, and that tells me the expected number of times I pulled each arm A times Kullback-Leibler. This is clear, right? So we get this lower bound, basically. It was not a big deal. So now we've got this lower bound. Again, this is telling us how much evidence we need to rule out options. So now we come to a lower bound optimization problem. So it's minimize summation NA subject to this quantity here. right? Okay, so I'm going to now simplify this lower bound a little bit to basically tell you how we solve this. But currently, this stuff was kind of spelled out cleanly in 2016 or so. And the algorithms that came out initially were plug-in algorithms that you kind of, at any time you are, I'll just come to that in a moment, but plug-in algorithm basically is that you give some samples to every arm, so you have some idea what these mu a's look like, right? So you have some idea what this distribution look like. Then you solve this optimization problem. Now you know what these NAs should look like. Now you chase them. You follow in that direction, give samples as per this recipe, get some more samples, update your mu i's, because you always worry that your mu's are going to make a mistake. So you update them, repeat this whole process. Repeat this whole process until you have enough evidence that you can stop. By generalized likelihood ratio test, I'll talk about that in a moment. And that's when you stop, that's the algorithm. That's what people were doing. It's very time consuming because you have to solve these optimization problems. So plug-in algorithms are kind of have this drawback. And the issue was, can one come up with nicer algorithms which exploit the structure? So that's where we are going right now. Okay, so again, simplifying the lower bound optimization problem. So this is what we have here. Now, what we'll do is, we'll break this into separate constraints for each arm A. So this is just looking at the set where arm 1 is lost out to arm A. So the bad set is that arm 1 loses out to some arm A. It's just a union of the sets where arm 1 loses out to arm A over all arms A. Right? So I can just break it and I can have separate constraint for each and every arm. And what I'll do is I'll assume that for now, just to keep the discussion simple, I'll assume that the distributions are restricted to single parameter exponential family. Bernoulli's, Gaussian with known variance, Poisson. The benefit of that is now I don't have to talk about probability distributions. I'll just talk about means, estimated means. So just single parameter. One can map it to just one parameter. So that makes the notation much simpler, the discussion much simpler. Towards the end, if we have time, I'll tell you how one generalizes these things to more general distributions. Okay, all right, so I've got these constraints. Now this infimum, it's actually, it's just, these are just real numbers now, mu1 and mu-a. So I can just find the derivative and solve for this. Turns out to be, it's achieved at point x1a, n1 mu1 plus na mu-a upon n1 plus na. Just an average of the two means. So I have a nice, now I have these k minus 1 constraints. If there are a total of k arms, I want to minimize summation na subject to these constraints. And these are like, the way to think about this is these are the indexes of each arm A. The bigger they are, the more convinced I am that that arm is not going to be the best arm. So I keep on sampling them. I just want enough evidence that each arm is not going to be the best arm. I want this to be greater than log 1 by delta. Then I'm convinced. Then I stop. So that's the general thinking. All right, let's carry on. So when do I actually stop? So this is generalized likelihood ratio based test. The idea, if you're seeing first time, it's nice to see this. You've seen this data, and you say to yourself, what parameters best explain this data? So you look at the likelihood ratio under all the parameters, the likelihood under all the parameters, and just choose the parameters which maximizes likelihood. So that comes here. So this will correspond to just parameters being their means. And then you divide it by maximum likelihood of the data under alternative hypothesis. If the alternative hypothesis was true, then what would be the most likely way of seeing this data? So that's the denominator. You look at this ratio. When this ratio becomes large enough, that's when you stop. So this goes back to Chernov's paper. I mean, Wald's work before that in sequential analysis, but Chernov's paper in 1959, very beautiful stuff. This ratio actually turns out to be exactly this, the quantity that we've been talking about, the lower bound that we saw. It's exactly this. So you stop when this quantity here becomes greater than or equal to log 1 by delta, and you have some smaller order terms to help with the analysis, to prove that actually probability of error is less than or equal to delta. So you can see that, this is, I'm going to stop and this becomes log 1 by delta. On a good set where things are well behaved, my mu hats will look a lot like mu. So when I stop, I'm more or less matching my lower bound. Right? So it makes perfect sense that this is what's going to happen. And this has been the spirit of algorithms. Proving these things takes some time and some effort, but it's not such a, it's clear what's going on. So top two algorithms became popular again, I guess 2015, thereabouts. Dan Russo was the main player, but there have been a lot of papers. I've just mentioned two here. But what was proposed was top 2 beta optimal algorithms. So they are gaining a lot of interest. So let me just tell you what they are. So IA is an empirical version of this index that we saw. At any time, we just have empirical data, right? So we have empirical idea what these indexes are. So if these indexes are large, then we are more comfortable that that arm is not the winner. If the indexes are small, then we are less comfortable, right? So please don't starve any arms. So that's a good philosophy generally. Don't starve people, don't starve arms. That makes perfect sense. So we do that here as well. So we're not going to starve anybody. So give enough samples to every arm so you're not being hurt by some very rare event. So if total samples you've given so far is T, make sure everybody at least gets root of T. That's a social security that we have here. That makes sure that on a high probability, you have a high probability set where things are well behaved. Now select an arm with largest sample mean with probability beta. And select a challenger arm with the smallest index, because smallest index is the one which is causing the most confusion. That could be the contender. That could be the best arm. You might have made a mistake. So you select that with probability 1 minus beta. Right? Just keep on doing this. So the simplicity is nice. At any time, pick an arm which has the largest empirical mean. That looks like it's the best arm. Very likely it is. Challenger arm, which you're most confused about. With beta, this guy gets a sample. With 1 minus the beta, this guy gets a sample. And you carry on. And stop when you generalize, like when all the indexes are large enough, you have enough evidence to convince yourself that, okay, I'm delta, my error is less than equal to probability delta. Right? Is this clear to all? Okay. So that's the idea. I'll just explain to you what's really going on here. But the problem with this was that beta was arbitrary. This was shown to be order optimal, but we didn't have guidance on what the optimal beta is. How do we pick all this? How do we think about this? So we'll talk about this here. But let's just talk about the problem first. So, this is an optimization problem, right? Minimize summation NA subject to these constraints for each arm. You can see that if any of these guys is 0, then this side is going to be 0. Basically, then you can't differentiate it with the arm. You just don't have enough evidence. Just from here, you can see if I put 0. So these are going to be strictly positive. And because they're strictly positive, they'll be tight. These will be equalities. Yeah. X1A? Yeah. So this was the one where we solved this infimum problem here. And we came up with this average between mu1 and mu a. Yeah. It just solves the infimum problem. So, yeah. So we reduced these uncountably many constraints to just one constraint. But yeah, so it's, although nu1 is lesser than nu a, but what's the most likely way that that's going to happen? Sorry, I didn't follow you. It's a number. So I'm looking at single parameter exponential families, so there's only numbers now. It's like, think of it as Bernoulli. Mu's are just numbers, yeah. So mu1 is a number, nu1 is a number, mu is a number, nu is a number. I optimize. Yeah, so this M is misleading. This should just be nu1 less than nu. Yeah. But I kind of first wrote this, then I wrote this. Yeah. So it's a number. Yeah. So there's a very interesting way to think about how to generalize this to other distributions. I'll briefly talk about it if I get a chance towards the end. But yeah, so this is the separation. This is kind of just defining, solving the optimization problem. Right. So now we know these are going to be tight. Now it's very easy to see if these are tight, I want to minimize this. I can reduce N1 and increase all these NAs so that this constraint remains tight. Or I can increase N1 and reduce these guys so that all these constraints remains tight. So at optimality, either of these things should not help me. You can see, right? I increase N1 by delta. I have to reduce NA by some number, which is delta times this divided by this. That will make this constraint have the same value. I can do that for each A, but that should not improve my objective function at optimality. And that tells you that this constraint must be tight. This must be holding. Because if this is not equal, then you can improve by playing with N1 and the NAs. Is this point clear? I mean, all of this you can use Lagrangian in optimization theory, but this is a very kind of straightforward, intuitive way of seeing it. There's a substitution element to it. So this is what we are really looking at. When we try to solve this optimization problem, it's this simple. We're just solving for this. And it's not difficult to argue that this is going to have a unique solution. So this is all we are solving here. So how does one find that beta? That was what we are trying to do. But this is telling us that really beta is one which kind of maintains this equality, which was something which was missed earlier. So our algorithm is as follows. So optimal top 2 algorithm. Let's denote this ratio sum empirical version of it, because this is what we'll be observing as we go along in the algorithm. Let's call it G. And let's call I of A as empirical index. For each index that we'll observe, let's call that I of A. So our algorithm is also, please don't starve any arm. If G is greater than 1, if this ratio sum is greater than 1, then you can, you should give samples to N1. That's going to, actually, this is going to be a monotone function of N1 is going to decrease with it. So that will push it down towards 1. If G is less than 1, sample arm with the empirical smallest index. So that's the algorithm, basically. Earlier, you were flipping coins. Now we're just saying, look at this ratio. If it's greater than 1, sample the best arm. If it's less than 1, sample the arm which has the smallest index. And stop when you, again, all the indexes are large enough so that you're convinced. So that's the algorithm. Why does this work? Okay, the point is this, let's look at these. We want all these indexes to be equal, even in our beta setting. So what you do is, whenever you give a sample to suboptimal arm, you give it to the smallest index here. So now the smallest index will have NA, which will increase by 1. Mu hats will perturb, but that's relatively a small perturbation. So you increase that arm, you become more comfortable with it. Then you'll give it to the next smallest index. So what's going to happen is you'll have some smallest index at some point. You'll keep on giving samples to it whenever the coin flip says that you should. It will catch up with the next smallest index. Now those two indexes are going to move up together, catch up with the next index. You can argue that the smallest indexes are going to move up together at a linear rate as you give samples, while the indexes which are not getting samples, they're also going to increase, but at sublinear rate. So they're all eventually going to meet. So that's the spirit of all of these. Even beta algorithms, what they're trying to achieve is, it's like bucket filling. You're trying to get these constraints to become equal to each other. That's what's really going on. So that gives us you an idea. This idea is probably something maybe which has more general value. Let's just see what the ideal system looks like. So under the fluid path that we create, empirical distribution mu looks like mu hat looks like mu, because with high probability they're very close. So let's ideally just assume that's equal to mu. Once G is equal to 1, it stays 1. So I told you that when G was greater than 1, we give samples to the best arm, it brings it down. When G is less than 1, you give samples to the suboptimal arm, it brings it up. These are monotone relations in ideal setting. So you assume that it's going to be equal to 1. I mean, the point is I'm creating ideal systems, and then I'll argue that the algorithm actually chases them. So, and once two indexes are equal, they stay equal. So once the two indexes are equal, they're going to move equal together until they catch up to some other index, then they'll move together, so on and so forth. But once I put these conditions in, then I'll be able to arrive at an ODE, which will tell me how these allocations are going to move under my algorithm, if these conditions are true. And then I'll argue that, okay, my algorithm is actually going to be very close to this. The two are going to move together. And the tool that's going to help me all of this is the implicit function theorem. So, I'll find that the Jacobian of these equations turns out to be actually invertible. So the picture clarifies. Let me just get to it slowly. But that's where we're going with this. So suppose after initial exploration, concentrated around mu. So that's the time you kind of start looking at the system. So at that time, suppose G is greater than 1, then you'll give samples to arm 1, and basically you make this equal to 1 in the ideal system. Now at that time, suppose your indexes look as follows. Then you'll give samples to this index. Your algorithm is, okay, this will fluctuate around 1. Whenever it's less than 1, you give a sample to the smallest index. So this will rise up, catch up with this guy. Now these two will catch up, they'll move together, they'll catch up with this index, and so on and so forth. And we can now find the ODs which are going to be satisfied, which will tell us how these things are moving together. Basically, as a function of, as I give my extra samples n, this constraint is going to be true, and these smaller indexes are going to be together. Other indexes I'm not touching. That's enough to tell me how everything is moving, how the allocations are moving. Okay, so feed arm 1 with minimum index while maintaining this. Recall these are the indexes. Smallest indexes increase at least linearly. You can bound these things. Larger ones increase sublinearly. Once they meet, they move together. And system becomes stationary once all the indexes are equal. So you can actually argue that all of this process is happening on a time scale which is independent of delta. So eventually all the indexes will become equal. Your G will be equal to 0. So you kind of met most of the requirements that you have. You got this to be equal. You got all the indexes to be equal to each other. They're just not equal to log 1 by delta. Then you just carry on with the algorithm. It will have a stable situation. Your OD will have a kind of a fixed point kind of solution to it. And you carry on until this condition is satisfied. So that's the fluid picture of what's going on. A lot of work goes into showing that the actual algorithm is close to the fluid model. It took forever to kind of get those things to work. But maybe there are simpler ways. Okay, so implicit function theorem is going to tell us that the fluid solution satisfies ODs concatenated together. So we just paste the ODs together. You meet two indexes. You have OD, which is telling you how these allocations are going to evolve, and meet the third index. Now you have 3 indexes. You have a different OD, which tells you how your system is going to evolve, so on and so forth. And the algorithm, after sufficiently large number of samples, closely tracks the fluid path. So that's the other part, that they're much going to be close, and then they're going to remain close. So that's going to help us. But essentially, so what we do is we reduce all the probability. We identify the tubes where the uncertainty lies, and then it's a deterministic analysis. So that kind of helps in some sense. For this part, now there are clever things you can do probabilistically when we go to more general distributions. I'll talk about that. Yeah, I should get time for it. Okay, so where are we? So yeah, so due to implicit function theorem, you have, let's call this n prime b as I give more samples to my system. So now with these equations fixed, if I tell you what my total number of samples are, these equations give me a unique solution of how much samples I've given to each arm, because these equations are true. So I know, and as my number of samples increase, these allocations are going to increase. So this is the equation they're going to follow, n1 prime, nb prime. So we don't have to look at the numbers, just that they're going to increase at least linearly. So that's what one gets from here. One can say more about the indexes which have not been hit, what ODE they have, and one can argue that this is going to come, these are going to approach them at a faster rate. Those are details, let's ignore them for now. Picture you can see in one simulation experiment that, okay, this was the smallest index. It rose up and caught up with another index, and then they moved together, and they caught up with a third index, and then they all three moved together. So this is exactly how things happen in the algorithm. So one sees that here. Any questions so far? Okay. But really, I mean, the big picture again is you just want enough evidence to rule out coins. Right now, we are giving samples to the best arm, and we are giving samples to the most challenging arm, and they're all rising together. And once the likelihood ratio becomes equal to log 1 by delta for each one of them, we are convinced that all of them have probability together of arriving at the wrong conclusion, which is less than equal to delta, so we stop. So that's the flavor of where all of this is going. Okay, yeah, simulation, okay, do it as well. So controlling the probability of error. So what I've said to you right now basically is I've given intuition that, if you do this chasing algorithm, or if you do this plug-in algorithm on a high probability set, you'll stop at the right time. You'll actually match the lower bound. So that's a theorem that you actually match the lower bound as delta goes to 0. So that's what I've shown you so far. But I'm not showing you that, how do we control that the probability of error is less than equal to delta? That also needs to be controlled. Again, this stuff, so this is our statistic, right? This is our statistic that we have. We are looking at new in the alternative set. Whenever this minimum becomes larger than log 1 by delta plus some small stuff, that's when we stop. That's when we are convinced that we got the right decision. So what if we made a mistake? What if when we stopped, we had made a mistake? In that case, this alternative set actually contains a true distribution. Right? We've concluded that third arm is the best one. Then first arm having the larger mean, the true configuration lies in the alternative set. Right? So I can upper bound this by this quantity right here. So I just put mu a, the true values here. So this event must have happened. Now this is nice to see. So when I made a mistake, I saw that this event here, this quantity right here, took a large deviation of sorts. Because you can see that mu hat a is converging to mu of a. Right? So this is going to 0. This together is actually going to 0. So this probability of this event happening is a rare event. So if I can control this probability, if I can show that this is less than or equal to delta, then I've proven the delta correctness of my algorithm. And it's kind of intriguing, this stuff. It's probably worth looking in for probabilists, because what I'm going to show you is a technique which is popularly used here, which works for all, no matter how I allocate. Whether I'm using plug-in technique to decide how to give my next samples, whether I'm using these top 2 kind of algorithms, any which way, all of these algorithms will have the property that this thing will be bounded by this quantity, and my technique will be to bound this probability by delta, no matter how my allocations NAs are chosen. So there's a uniformity to it. It's nice stuff for people, it's something to think about. Can one make it tighter? People think a lot about this, but this seems kind of non-trivial. So how do we do this? So dual representation, exponential concave inequalities, and mixture martingales. You use them, and that's how this works out. But let me tell you some nuts and bolts of this. And let me tell you this now in a more general setting. So a lot of you are bored, you just told us about Bernoulli distributions, kind of insulting us. So let's look at slightly more bigger class of distributions. So these are probability distributions whose 1 plus epsilon moment is bounded by B. So this B, no B. So now I have these K bandits. All I know about them is that they come from this family. Their 1 plus epsilon moment is bounded by B, and B is known to me. In that world, I want to find the best arm. Is this clear to everybody? That all we've done is we just changed Bernoulli's to more general distributions. This is what we know. We know this B. And nothing really changes much in some ways, because now I'm just going to define my KL infimum mu AX. So mu A is my arm A distribution. I look at all the distributions whose mean is bigger than X. And amongst them, I'll find the one which has the closest to mu of A in this Kullback-Leibler sense. And that becomes KL infimum mu A to X. So this tells me a distribution which is, in terms of means, its mean is at least X. So that's how I'm going to use this. I won't make a big deal of this right now. I'll just, everything I've shown you with all those equations, wherever I had KL, I can plug in this KL inf. And that goes a long way. That kind of sets everything up. The only thing really changes in my analysis is proving delta correctness. That's where I need to be far more careful. So I'll throw light on that right now. But first of all, why do I need this condition? So why do I need this B to be known here? Why can't I do this for any distribution at all? So you can check here that it's easy to find 2 distributions whose Kullback-Leibler distances are arbitrarily close, but their means are arbitrarily far. So some distributions are unlearnable. You can't learn them from data. You can't say this arm has a higher mean than this, because one large sample will come later, and that will change your conclusion. So because of this, my KL in for these guys is going to be 0. So for those of you who are used to seeing Gibbs measures and all that, in Gibbs measures, I'm keeping this fixed and optimizing on this argument. This in the large deviation setting. So yeah, so that's a very different flavor thing. Then you have exponential twisting as the answer. While this quantity here, even when my class L of these distributions is fat-tailed, even then this will give you a positive quantity here. I mean, as long as I have this bound here, B. So that's the because you get a different kind of twist when you minimize on this argument. So anyway, so because of this, so that some restrictions is necessary. So that's why that B is put in just because of that. That's why we're going to look at this family. Okay, now what is my KL inf here? So it's just infimum over all distributions kappa. I'll just do this in discrete setting, right? I'm trying to minimize this objective. I have this 1 plus epsilon moment constraint. I've imposed this constraint. I'm looking at all distributions whose mean is at least X, and these are probability distributions. So this is a convex program one can solve through Lagrangian duality. I'll just bore you a little bit with what do we get from all this? Where am I going with all this? So what we get is that the duality will tell you that there are 2 Lagrangian variables, lambda1 and lambda2. So this dual is expectation under this measure eta. This is KL from eta distribution. Right? That's a 2 distribution. I'm looking at all the distributions which minimize which have a mean at least X, and they are closest to their mean is at least X, and they satisfy this moment condition. So they turn out to be this turns out to be alternate representations. So expectation under eta, these are parameters lambda1, lambda2. You can show that this set is going to be compact. So it's a maximum of this expectation, and then you have these parameters lambda1 and lambda2 here. I'll just explain this in a moment. When we do the algorithm, we're not looking at this expectation. We are looking at empirical distributions. So we are really looking at this quantity right here. And really, this is empirical KL inf. Remember, I'm just worried about this probability. I want to show, this is when I stop, and if I make a wrong decision, my probability of making a wrong decision is upper bounded by this quantity right here. So this is what I'm concerned with, except I have KL inf here. So I want to show that this probability is small. So I'll argue for you that each of these terms I can upper bound by a super martingale. And then sum of super martingales is again a super martingale, and I can use Wheel's inequality. And that helps me come up with any times bound for these things. Because again, there's a lot of kind of stopping times, adaptiveness, but Wheel's inequality, I don't know how many of you have heard of Wheel's inequality before. You must have, right? So it's not sub-martingale inequality, but it's a super martingale inequality version of it. So it's now become very popular in learning theory. I'll just show you as we go along. So that's going to help me. So I'm going to show how each one of these terms can be bounded by a super martingale, then the sum can be bounded by a super martingale, and that helps me then bound this probability. So that's a big idea here. All right, so this is my KL inf again. So I have this representation here. The problem is this. See, these are xi's are the samples that I've generated right now. I've generated for each arm. I'm just focusing on one arm right now. I've generated NaN samples, and these are actual samples that I generated. These are dual variables. If I was just looking at this, I could apply Chernov's theory to get bound on these kind of probabilities. That would not be a problem. But now I have a maximum over here. These dual variables, I'm looking at maximum over a compact set. So now one can construct an epsilon net to deal with this maximum. That could be one way, but that's slightly inelegant way of doing things. The elegant way turns out to be using this, sum of exponential concave functions. They have a useful inequality. It's a nice inequality. I think Kober in his book on information theory suggested this, but then Santosh Vempala and others in computer science came up with it. But it's very nice. So let me just show this to you. So suppose lambda is a compact and convex subset. Q is a uniform distribution on lambda. GT is any series of exponential concave functions, meaning if you exponentiate them, you get a concave function. See, if you exponentiate these guys here, this log here, then in lambda 1, lambda 2, you get a linear function, which is a concave function. So that's where I'm going to use this. So then, if I'm looking at this sum here, and maximum over all lambda, I can upper bound this by log of exponential of this exponentiated summation GT lambda, plus some small terms. The point is maximum, so this is a mixture here. So mixture will always be dominated by the maximum, but can we go the other way around? Can we dominate the maximum by a mixture by paying small penalty? So that's what this is buying us. So this is maximum here. It's being upper bound, if you just exponentiate this, for example, then this becomes just a mixture. So it's going to be smaller than this quantity, but the other way around we get by just paying this extra penalty, this right here, which is not much of a penalty at all. So now the advantage is this is the term which I don't want to deal with. This is a mixture term. So mixture of super martingales is again now super martingale. So that becomes very useful to me. Okay. So the mixture of super martingales. So now, okay. So now I guess where I'm going with this, I'll just summarize quickly. So each of these terms I'm going to be able to show is dominated by a super martingale through this mixture over dual variables. And then the sum will be dominated by a super martingale. And now I'm going to use this Wheel's inequality. So if you've not seen this, so if Mn is a non-negative super martingale, then any time it exceeds x is dominated by E of M0 upon x. It's a very simple proof, but somehow this inequality is not used very much amongst probabilists. But I guess now when we try to come up with very tight confidence intervals, because everything I'm saying is in a way of coming up with very tight confidence intervals of sample averages. So this inequality is the key for that. Okay, so that's all I had to say. So with this, you can get delta correctness in this generality. Even these top two algorithms that I mentioned, all the equations that I've been showing you earlier, these optimality equations, like these kinds of things. If I put KL inf here, KL inf here, KL inf here, KL inf here, everything goes through. A lot of analysis goes through, a lot of work goes in showing that the algorithm chases the fluid limit. And then once they're together, they stay together by the implicit function theorem kind of analysis. But that's where the challenge is, and that work becomes more complicated when you have general distributions. Okay, so that's all I wanted to say. So my conclusion is we discussed the best term identification problem, applications, and a popular algorithm, just through tubes. Then we introduced the optimal top two approach and discussed its fluid behavior. Presumably, this kind of fluid behavior comes up a lot in algorithms. Ideally, they equalize things and they move together. So then the underlying ODE one can identify. So we argue that our algorithm closely tracks the fluid behavior when generated samples are large. And we outlined how delta guarantees are obtained using duality and the supermartian analysis. Thank you.
Any questions?
So in the last part where you had the top two algorithm and in the space where you're looking at very general distributions, it wasn't clear whether you actually approach the constant, the best constant.
You do.
You do.
You do, yeah.
If you replace the k-linf in those arguments, one of the things there is that x1a, which is for a parametric form.
That's right, yeah.
But in the infinite dimensional setting, what would
it's again, you differentiate and you get that solution. And now you again do implicit function theorem on that, and you can get an order of magnitude of what that looks like. I mean, in the earlier case, when I have N1 and NA, it was the average of these things. In the analysis, the key concern is when is the average close to one side or the other? Because otherwise, the analysis kind of goes through if it's order one. So that we can do in generality. And the tool we use it kind of, again, implicit function theorem, so we can write it as its derivatives in terms of other things.
Any further comments, questions? Okay, if not, let's thank the speaker again.